Alright, today I'm gonna do a tutorial on how to do a self-playing pinball game, like you see on the screen here. This game is gonna play for over a minute, but I'm gonna talk about how to set up a problem like this. Basically, as the ball gets close to a certain contact, uh, it's going to activate one of the boundary conditions. And the boundary condition you can activate in this case is basically rotation of the rigid body, right? But you can also activate many other different type of boundary conditions. And that's the beauty of this example is that it sets up the stage uh, for a lot of different other problems. Okay, let's take a look at how we do this. All right, so I have the example problem here. I'm going to look at how to do this one step by step. Okay. Okay, so this problem is actually pretty simple. It's a 2.5D problem, but basically I'm setting everything to move in the YZ plane. Okay. And then this right here is the ball. I'm gonna set it up. There's a couple different material that I'm assigning to these, right? I tried out a lot of different options, but I'm gonna use a specific setup to run this. No, everything here is mostly just obstacles. This bottom wall right here, as soon as this ball hits the bottom wall, it's gonna terminate the job. But when the ball hits one of the flippers, the flipper is gonna essentially angularly rotate, and then that's gonna basically keep the game going. Okay, so to set up something like this is a pretty standard sensor problem, right? But you can do this for a lot of different other things, right? So if you look at my previous example about sensor activated functions, there is a lot of different things that we can activate in terms of a sensor control that let us activate a bunch of different things. So in this specific case, what we're activating is one of the boundary SBC options for our problem. I'm sorry, boundary prescribed motion for our problem. Okay. All right, so first thing we want to do here is I'm going to turn everything rigid, except I'm going to turn everything rigid except for the ball. Okay, because in this problem, the ball is the only thing I'm allowed to have some stiffness, um, right? And you can sort of see for actually it does this a lot. It's a weird thing that it does. It doesn't actually show the coordinate system. But one thing that you want to sort of see is that this is the flipper 2, and this is the flipper 1. And what I like to show about these flippers, right, is that if you actually take a look at the inertial coordinate system that's created by Workbench, that is actually the rotation joint that we're generating. Because when we generate a boundary prescribed motion rotation for one of the rigid bodies, it's by default it's going to rotate relative to the centroid, to the CGs. And then that's the one thing we wanted to do. Now in terms of for the ball, I'm going to use the actual ball material. Now this ball material is basically the steel material, right? Except I intentionally made it a lot lighter, right? To make the ball basically move a little bit better. And that's sort of what I'm doing here. 1 second. Okay. And everything else is also a rigid body, as I've essentially described. Okay. Now the next thing we wanted to do is let's go ahead and create a contact pair. So I already disabled the body interaction. I don't want that contact. And then what I wanted to do next is I want to go ahead and just merge all of the bodies where possible, right? And I think in this example problem I actually already know merged everything, I believe, but I can test it out by just doing a quick auto contact to see what shows up. And I think the only thing that showed up is between the bottom surface right here. Yeah, but this actually doesn't matter so much because I'm gonna actually fix everything. So this contact doesn't need to be there. But for sake of simplicity, I can go ahead and just suppress it. I don't really need this. Okay, but what I do want to have is to define a couple contact pair, right? The first contact pair is going to be between this ball. Let's do a frictional contact. And this flipper. And I'm gonna do say 0.2 and 0.15. Okay, and then this is basically the first frictional contact pair, and I'm gonna do one more frictional contact pair, which is between this flipper and this ball and this the other flipper, right? Notice the ID of 81 and ID of 78, right? These two ID I'm actually going to use in a second to set up my problem. And then the last thing, of course, I want to set up a frictional contact between the ball and the bottom surface, right? And this has an ID of 84. These three right here are going to be things I'm gonna use as a target of the sensor to activate certain aspect of the sensor. Okay. All right. The rest of it is that I'm going to basically mesh this thing with a 2mm mesh. Keep this thing super simple. I can make the jaw here a little bit better, but I think it's okay because I already made these rigid, so they don't really do a whole lot. So this is likely gonna be all right. Okay, and what I do like to do is to check my sizing, and I can actually defeature a few things here, but I think we're okay. So we're okay for now. All right. Okay. Next, what we wanted to do next is to look at let's go ahead and set up a couple basic things. All right. The first thing we wanted to sort of set up is that we want to make sure the ball is only allowed to move in the YZ plane, which means I'm gonna essentially constrain any kind of out of plane movement. I'm gonna set this to 0, and that basically constrain the ball so you can only move in that direction. And what I also like to do is to create a rigid body constraint for everything else, right? So for example, if I want everything else to be fixed in place because everything else is a rigid body, what I can do is I can select all of it and then go to my and then over here I can set a rigid body constraint, and that's gonna basically constrain everything. And then I'm gonna remove the reason that it's yellow is because this object's in there. Okay, that will constrain everything, all the rigid body that's in the model, so they can't move anywhere, right? All right, and then what we want to do next is apply a gravity. Now the gravity we're applying here, right, is that we actually need to, one second, we actually need to apply it to just one body, right? Second. So what I'm going to do here is I'm going to do a low body Y. Alright, so this low body Y is going to basically assign. So this is basically the keyword that I essentially created, right, to sort of calculate, to apply the low body Y. But in this case, what I wanted to do, right, is to actually apply the low body to a specific body only instead of to everything. I think in a way I could have just done using using the center Earth gravity that will also apply to everything, right, to all the body. But in this case, because I only wanted to apply to the ball, right, because when the flipper moves, I don't want the gravity to affect it. So in that case, that's why I only apply the gravity to the ball. So I have a low body part of 9999. So what I wanted to do next is to go ahead and set this part to a name selection, right, and then assign this an ID of 9999. Right, so what this does is that you assign that ball to 9999, and it ensures my low body parts only calls out that specific part, right? And then he's gonna apply a y direction gravity load based on this load curve, which is essentially just gravitational acceleration across the whole body the whole time, and that's what's gonna initialize the movement of the ball as it travels downward. Okay. And one other thing is that I actually wanted to create actually need to unselect this because I actually want the ball to hit all the other objects, right, which is why I actually have an all body here with this. What this turns into is a single surface contact, single surface 005, which is going to cause the ball to contact everywhere else. Okay. All right. So with that, that's the basic model setup, right? Basically, what happens here is that as the model starts, it's going to drop down, it's going to start hitting everywhere. until, and then you will have no termination unless you reach the termination time. For me, the termination time in this case, I'm going to set something to be super long because I'm going to terminate it with a sensor, right? So I don't want to terminate prematurely. And then I'm going to basically allow the model to just run essentially forever. Okay. All right, so the next thing I wanted to do is sort of, before I define my sensors, right, I want to tell the flipper to move in the way that I want it to move, right? So what we wanted to do next is to actually create a remote point movement for these bodies right here, right? So a standard way to do this is to do a boundary prescribed motion, right? So what we wanted to do in something like in this case, right, is that we actually just wanted to define a set of vectors. So I have a template which basically defines a set of vector, right, and it defines a set of boundary prescribed motions, like this one right here. Okay, so this whole template looks like it's a lot, but basically what it does is that it defines 6 different vectors, right? One is in first set of vectors is in the 1, 2, 3 location, and it's gonna call out a coordinate system ID here, and this is ID is what I'm gonna actually modify. So if I look, so the question here becomes, what is the coordinate system ID that we want to use? We can use 0, right, in this case, because we're just using the global coordinate system ID. So I can change all of this just to 0, right? And what is it gonna do is that it's actually gonna use that coordinate system ID 0 to define the x, y, z coordinate system. So in this case, the coordinate system ID here is gonna use this is the x-axis, and that's actually what I'm gonna be rotating at. Okay, and then I only need this 71, 70, 703, this type of ID, and I actually don't need this pair. I'll delete these. Okay, and then over here, it gives me what I'm looking for. So this right here gives me the low curve, which is 0, 0, 0, and that's where I'm gonna constrain the rigid bodies, right? Yeah, I actually forgot to do something. 1 second, I actually forgot to do something. I just realized I need to unconstrain these two, because I actually constrain a little bit more than I should. Okay, now it's good. Now what I can also do here is that I can actually create another rigid body constraint. Okay, let's do it. Let's do it my old way. So what you can do here is also create another set of rigid body constraint. Right, rigid body constraint, and then just scope it to these 2 bodies and make sure the x-axis is free. You can certainly do that. That will be one way to do it, right? But in this case, I'm actually going to suppress this. I'm going to do it my old way, which is actually using a keyword template. So you think this keyword template creates 3 different vectors in the global XYZ direction. So this is X direction, Y direction, Z direction, right? And it's going to basically call out a low curve, which is 0, and it's going to constrain everything, right? So what I'm going to do here is I'm going to do boundary prescribed motion rigid across the board. And then if you look at the flipper ID is 1, 2, 3, 4, 5, 6, 7, 8. So flipper 1 is 8, flipper 2 is 9, right? So I know that because that's how Workbench works. That's how they name parts, right? So basically, when I do boundary prescribed motion rigid with a part ID 8, right? And what that's gonna do is gonna call out rigid body ID 8, part ID 8, and it's going to basically define a constraint based on low curve 900, which is 0, 0, 0, and it's gonna constrain 3-degree translations and 2-degree rotations, and leaving the x direction free. And for the x direction, I'm gonna define a rotation through the bottom part here, and it's gonna have an ID of 101. Okay, so what we did here is these 5 boundary prescribed motion rigid constrained based on this low curve, and based on a specific curve ID 70, 71, 2, and 3, right? So these are the 3 different vectors in 3 different directions, translation and rotation. And then for the x direction rotation, which is going to be controlled by this card, I'm going to cause it to rotate, and then this VAD equal to 2 means it's a displacement, and I cause it to rotate by this much radian per second, which I think is like 30 degrees or something like that. And it's going to basically rotate this part from 0 to 0.001 second. It's going to rotate the flipper by this much. The rotation axis will be the CG of the rigid body. Okay, so that seems like a lot based on just essentially code, right? But once you get in that familiarity with Dyna, you can just basically, for me, this is just like reading code for me. But essentially all you're doing here, you just apply a boundary prescribed motion across the CG and rotate that by this much from 0 to 0.001 second, and it's going to immediately return the flipper after 0.01 second delay. Okay, right? The reason this is important is because this is the thing we're going to control with ID 101. This is the thing we're going to control with and this is going to be ID 102 with sensor. And then ID 102 is very simple, right? You got exactly the same keyword, exactly the same well, actually I don't need to do this. I should just do it this way. I should just create another bottom part like this. Okay, I'm gonna call this the 102, and it's gonna call out the ID 9, and it's actually gonna rotate exactly the same way. So in this case, I actually have to do this. So hold on one second. I'm actually gonna do this. So I'm actually gonna create another set of constraint, and in this case, I'm gonna do 9, 9, 9, and that's gonna constrain the flipper number 2, which has an ID of 9, and it's gonna basically call out the same low curve. Actually, I'm gonna call out a different low curve. I'm sorry, because it has to be in the opposite direction, because essentially flipping in the opposite directions. But this one will have a negative number that we're gonna want to assign to, and that's essentially what's happening here. Okay, and that's what's essentially so this we're gonna have a low curve of 902, and it's gonna call a curve a low curve of 902. And so flipper number 2, which is essentially this flipper, is gonna rotate in the opposite direction of the flipper number 1, which is why I have an opposite sign here, right? But it's gonna be constrained by the same low curve 900, which is 0, 0, 0, and he's gonna call out the same vector because it's based on the global direction vectors. And then this is basically gonna rotate the other flipper in the opposite direction by the same magnitude. Okay, it seems like it's a lot to digest with this keyword, but remember all we're doing is apply constraints through these 5 cards based on these 3 vectors, based on this low curve, and we're gonna apply rotation based on this low curve in 2 different parts. The first part is gonna have a part ID A, and that's gonna be rotating in one direction, and the other one's gonna rotate in the opposite direction by the same amount. And that's how we control the flipping of the flippers. Okay. All right, so with that, we'll have essentially the thing that we are using to basically control the motion. So what we wanted to do next is obviously gonna try to detect the contact between the ball and the flipper, and once the contact is detected, we're gonna flip the flipper. Okay, so the first thing we're gonna do here is let's do a sensor define force. I'm gonna call this the force 1. Right, now if you follow my previous video, I have a pretty standard template for define sensor force. So in this case, it's the same template. I have another 3 different vector. These vectors are also going to be based on global coordinate system. So technically I could use the same vector as I defined for the previously, but in this case, just to be consistent, I'm going to define it this way. Remember, this is just a direction vector. The origin is always going to be rotated relative to the centroid, and in this case, the contact force is going to be based on the global coordinate system, essentially, right? That's what I'm doing here. And then what I'm also going to do here is that I'm going to call the FVID Y, which is going to be the Y-axis here. That's going to be the direction in which I'm detecting the contact force. This F type tells us that I'm looking for the contact force. The contact force is going to be from the RC fork, right? And I'm going to call on the type ID. Essentially, in this case, it's essentially going to be 101. 1 second, okay. I'm double checking something. Oh yeah, it's actually gonna call out this ID right here, which is this ID, which is gonna be ID of 78. Yeah, it's not 101. I'm like, what the hell is 121 come from? Yeah, 78 right here. Okay, and this 78 corresponds to the ID right here. That's the ID that as soon as this contact force is detected between this contact pair, this sensor is gonna activate, and it's gonna basically measure the contact force in that pair. Okay, and then we're gonna do the same thing. We're gonna do sensor switch 1. All right, okay, guess what happens here? The sensor switch is going to look at essentially the sensor. All right, so let's look at the top one. The sensor switch is gonna look at basically the sensor ID 201, which is this one. I'm gonna call this ID 201. and the switch is gonna be ID 301. So the sensor switch ID 301 is gonna call out sensor ID 201, and it's gonna check if the contact force is greater than 1 × -5, which is some trivial number like 1 × -5 newtons. As soon as the contact is detected, the sensor switch is gonna get turned on. Okay. Now the second sensor is the tricky part. This is the part I learned from the dynamo presentation, right? Is that in order for the boundary condition to return, you have to turn off the previous sensor, right? Which means we have to define a condition in which we want to turn off the previous sensor, right? To turn off the previous sensor is where we want to create a delay of 0.01 and saying that as soon as the contact force is less than 0.01, it's less than 1 × -5, you're going to turn off this this switch, and turn on this switch, right? And that's going to essentially cause you to be able to flip back and forth between those two switches, which is why I want a delay of 0.01, because this delay of 0.01 is going to allow us to basically turn off the previous sensor and allow the flip to have enough time to come back. And this is the little trick that we have to do to be able to sort of look at the correct behavior for the flipper to cause it to have enough time to come back. So one thing what we can do here is to actually check the documentation. I'm actually going to check it live, right? Right. So sensor switch right here, this right here. Yeah, so the trigger to status change when the value given by the sensor is less than or greater than the value of the duration defined by T1. Yeah, there we go. So what this essentially does is that it gives that's the 0.01 second duration is how long this sensor is going to be activated, right? So when the contact force is less than 0.0, well, less than 1 × -5, which means the ball is bouncing away from the flipper, right? It's going to switch to this sensor. But this sensor is only activated for 0.01 second, which is what allows you to not constantly flipping back and forth of that flipper. So you only give that flipper 0.01 second to come back. And that 0.01 second is also where I describe it here, right? So this is how long I've given the flipper to come back. So this number aligns with this number because I want the flipper to basically have this much time to come back. And then this is also how long this switch is gonna stay activated. Okay, and that's basically the trick that we're playing. We're causing the switch to go to here when the contact is established, but as soon as the bound is bouncing away, it's gonna switch to here. But this switch is going to be activated for 0.01 second, which is how long it takes for that boundary condition to essentially return to 0. And that's how you can get the ball to bounce into the flipper and bounce back, and then the flipper can behave correctly and only flip once. So this is a little trick. So take a moment to think about this. It took me a while to understand how they did this, but I copied this from a dynamo presentations. And this is a very interesting trick that we can do for really a non-industrial problem, right? But this is something that's relatively interesting that we can think about. Okay. All right, so obviously once we have the sensor switch, we want a sensor control. The sensor control is basically going to define what we're moving, right? So as soon as the 301 and 301 is established, it's going to move the boundary condition to the pressed mod is the boundary prescribed motion, which is right, where is my pressed mod? Right here. Where's my press mod? Let's see, type. I can't find my press mod. Yeah, something's wrong with my template. Let me double check this. I mean, I'm going a little longer than usual for my video, but let me double check this. Press mod. Yeah, no. Oh, right there. Right there. Yeah, right there. So somehow I missed that. I missed that little. Yeah, so it's not it's not in this card, but it's in the other card. Okay, so just my template wasn't very clear. I need to fix my template on here. Okay. Basically, right here. I'm sorry, I actually missed it. Yeah, so it's just a different card. So this press mod right here is what we're essentially controlling. Now this press mod comes from this right here. So you have a boundary prescribed motion 101 that controls the left flipper, and you have boundary prescribed motion 102 which control the other flipper, right? So what we did here is that because I'm using the contact ID for the first flipper, I'm also using the sensor control for the left flipper. In this case, it's 101, right? Now this n rep equal -1 means I'm going to flip between these two switch over and over and over, right? So I'm going to start it. I'll start with none of the flip switch being turned on. As soon as the contact is established, I'm going to turn on this one. But as soon as the ball flies away, I'm going to turn on this one. But this one only lasts 0.01 seconds. And then back and forth it goes. Okay, so basically it allows us to basically every time the ball hits the flipper, it's gonna go here. Then very quickly afterwards, it's gonna go here. And then for 0.01 seconds after that, it's gonna turn off that boundary prescribed motion. About 0.01 second is how long it takes for the flipper to go back to the original position. And that's how this control card, the sensor control card can keep going back and forth, back and forth, back and forth. Okay, now this right here define my sensor for the left switch, left flippers. And then guess what? I'm gonna do exactly the same thing for the other one. I'm gonna do 202, which in this case is gonna be it's gonna be 202. And then the contact ID is going to be 81. Right, that's basically the sensor contact force for the right switch. And over here I'm gonna do 303 and 304. And then I'm going to basically call on sensor ID 202. Same thing, right? It's gonna flip and then it's gonna flip again. It's gonna switch this one and then switch this one right afterwards because the ball flies away. And then this one's gonna last for 0.01 seconds, which is how long it takes for the boundary prescribed motion to return to 0, right? And then it's gonna have a control card, which is gonna call on the type ID 102, and type ID 102 is the other flipper right here. Okay, and it's gonna have a control ID of 402. Actually, I'm gonna make it 403 to be consistent with my prime example, and I'm gonna call this the sensor right flipper. Well, lastly, all we need is a termination condition, which is when this one hits here, we'll have a termination condition. So let's go ahead and drag this out and create another set. I'm gonna call this the 203. All right, I'm gonna call this the oh, I think I actually need to get my vector. I need to delete this vector because these vectors are redundant, so I don't need this vector to be here. That's a good point. I can also either change their ID or use the same vector that I used previously, which I think that's what I would do. I would just not use the same vector. Although technically I need to be changing the vector's ID, but in this case I don't want to do that because they're the same vectors, so I can just leave it. And then in this case I can change this to 203, sensor ID 203, sensor ID 201. Sensor ID 202 and sensor ID 203. And then I'm gonna call the contact pair on this one to be 84. And that's gonna be basically calculate the contact force on the between the ball and the bottom surface, which is this contact pair right here. Okay. All right, and then the switch is gonna be slightly simpler in this case. The switch is I'm only using one of them. I'm just gonna copy all of these and I'm gonna call this the sensor switch ID 303. Oh, 305, and then because it's 1, 2, 3, 4, 5, I'm gonna call this the 1, 2, 3. That's fine. And then this is gonna be 203 here. In this case, I'm also gonna use the same greater than 1 into -5 as my. But in this case, I only have one because as soon as the ball hits the bottom surface, it's gonna terminate a job. And obviously, I don't need this anymore. And what I do need is a termination sensor card, which is gonna terminate the job. And it's gonna look for the switch ID 305, right? And then this right here corresponds to the sensor termination bottom surface. Game end. Okay. All right. So with these three, this three set of sensor is gonna basically the ball is gonna hit the bottom surface and it's gonna terminate the job. That's essentially what it is. Okay. All right, after all of that, we're essentially done. Obviously, if you follow my previous video, what I always do is I turn off the default control cards. I also turn off the default database cards. And then what I wanted to do is to actually write out my own database and control cards. But in this case, it's because the nature of the problem is very, very simple. All I have to do is to define a D3 plot, which is just a 1 united 3 D3 plot. I don't actually use any control cards or database cards. And that right there is the full result for the self-playing pinball game. If you follow my steps, you watch my keywords, and you should be able to replicate this, and you can create your own. But replicating this is hardly meaningful. What's meaningful here is to think about how many little tricks. This is the last part of my sensor video, right? But the beauty of sensor, that's why I spent 4 videos on this, right? Is I realized there are so many different ways in which we can apply this sensor-based technology or the sensor-based sort of techniques to different problems. In this case, I use 3 different sensors to control the left, the right, and the middle. And I use a special logic, follow the Dynamos example, to turn on, turn off a specific boundary conditions based on a trick and a delay that I can essentially add. This little delay or this little time duration of the sensor allows me to basically give the boundary condition time to return to 0, so I don't just leave it in where it is, right? So when I turn off the boundary condition, right, it's not gonna just floating in the air. I keep going. It's gonna return to 0 before I let it be turned off, right? So this is how I basically turn off something in at the right time with the right amount of delay. And that's a little trick is really, really interesting. And then what we can do is control a lot of different boundary conditions, right? So if you look at the template right here, you have so many different type of sort of, if you look at control here, you have so many different things you can control, like CNRBs, you can control contact, you can turn on, turn off contact, you can turn off support, you can turn off rigid wall, you can turn off different pressure loads, boundary progress motion loads, different curves even, right? So there's a lot of little trick. You can also do functions. I haven't made an example about functions because it's hard for me to think of one on my own, right? But knowing that the capability exists is what gives Dyna a lot of options to solve all kinds of problems in the world. Like simulation, as we do it, right, is never really tied to one product, even though that's how we do it inside a company. As a capability, I don't think it's ever tied to a single product. And the sensor demonstration shows that you can apply this technique, this thought process, this technique to many different applications, which is what makes it valuable. And then of course, ultimately what you get is essentially a self-playing pinball that goes essentially forever and ever and ever, right? And you get some really interesting behaviors that we can play with. Okay, I hope this is helpful. That's a relatively long video today. Thank you very much.